Welcome to the Deep Dive. We're here to get into the thick of complex topics and, well, pull out the insights you need.
Glad to be here.
Today, we're looking at something called the three-body problem. Now, maybe you've heard of the novel or the show, but we're talking about the actual physics, the real challenge in astrodynamics.
Exactly. Not the fiction, the gravitational reality. And what's really interesting, quite exciting actually, is how new research is looking at moons.
Moons, how do they fit in?
Well, they were often seen as just complicating things, another variable in that tricky three-body dance. But it turns out their gravity might be a massive help for space exploration, a real game changer.
Okay, so that's our mission for this deep dive then, to figure out how this gravitational puzzle isn't just a problem, but maybe an opportunity.
Precisely. We're going to explore how it could lead to potentially really big cuts in fuel costs and unlock totally new ways to get into stable orbits.
Especially around planets with lots of moons you mentioned, like Jupiter.
Jupiter is the prime example, yes. So think of this as your fast track to understanding some really cutting-edge ideas in space travel.
I like the sound of that. Hopefully some aha moments about maybe getting to the stars a bit more affordably.
That's the goal. Cheaper, smarter space travel.
All right. Let's start with the basics. The big hurdle, the high cost of deep space. Why is it so expensive to get out to, say, Jupiter or Saturn? It's not just the distance, is it?
No, distance is only one piece. The real energy sinks are twofold. First, you've got to fight your way out of Earth's gravity well. That takes enormous power.
Okay, escaping Earth makes sense. What's the second part?
Then, when you finally get there, light years away practically, you can't just, coast in. You're traveling incredibly fast. You have to hit the brakes hard.
So slowing down to actually stay there to get into orbit.
Exactly. And every single burn, accelerating out, decelerating in, adjusting trajectory, it all costs fuel.
And the mantra in space is?
Fuel equals mass, mass equals money. Lots of money.
So how much money are we talking? If you save just a little bit of fuel, does it make a real difference?
Oh, absolutely huge. Even tiny fuel savings, tweaking an orbit just slightly, can save tens, sometimes hundreds of millions of dollars on a mission budget.
Wow. Hundreds of millions.
Which is why finding these fuel-efficient routes, these clever orbital tricks, is so critical. It can literally be the difference between a mission flying or staying grounded.
Okay, so fuel is king. We need smarter ways to navigate. That brings us to gravity assists. Most people probably think of the slingshot effect, right? Using a planet to speed up.
That's the classic use, yes. We've been doing that for decades. Voyager famously used Jupiter and Saturn like that. You steal a tiny bit of the planet's orbital energy to get a speed boost.
But you mentioned innovation. It's not always about accelerating now.
Correct. The twist here, the newer thinking, is using that same gravitational interaction not to speed up, but to deliberately slow down, to shed energy carefully.
Using gravity as a brake, essentially.
Precisely, a space brake.
Is there a mission doing this right now? A real-world example?
Yeah, the Bepi-Colombo mission, the joint European and Japanese probe going to Mercury. It's a perfect case study.
How so?
It's using multiple flybys Earth once, Venus twice, and then Mercury itself 6 times each one, designed to chip away at its speed, bleeding off energy so it can eventually ease into orbit around Mercury without a massive fuel burn.
That's clever. Multiple small braking maneuvers instead of one big one.
Exactly. Which naturally leads to the question, if this works so well for inner planets, what about the giant ones, the ones with all those moons? Could we scale this up?
Right, Jupiter's system, Saturn's, all those potential gravity partners. So how does this actually work? You mentioned weak stability boundaries. What are those?
Okay, WSBs, weak stability boundaries. This is some of the key theory behind it. Imagine you're on a river, and there's a spot where the current is really weak, almost still, right next to a strong current.
Okay, like an eddy.
Sort of, yeah. In space, WSBs are regions where the gravitational pull from 2 bodies, say a planet and its moon, or 2 moons, almost cancel each other out. They're like gravitational calm spots.
And why are those useful?
Because if you can nudge your spacecraft into one of these WSBs, you can transition between different gravitational regimes, like moving from being captured by the planet to orbiting a moon or vice versa, with very little fuel. Tiny pushes instead of big burns.
So they're like low energy transfer points.
Exactly. Minimal effort transfers.
How do scientists even find these points? Space is big.
Well, they use mathematical tools. One powerful one is called Poincare mapping. It's kind of complex, but think of it like charting currents.
Charting gravitational currents.
In a way, yes. You track how an object behaves over time as it repeatedly crosses a specific imaginary line or plane in space. By plotting these crossings, patterns emerge. Hidden pathways.
Pathways to stable orbit.
Pathways that lead towards long-term stability with minimal energy input. Now, here's where it gets really interesting with moons. When you just have a planet in the sun, you have a certain number of these WSBs, these pathways, but when you add a moon into the mix,
It gets more complicated.
it gets richer. The moon adds its own gravity, creating many more WSBs, many more potential pathways. It's not just adding one more option, it's like the number of possible routes explodes.
So each moon creates a whole new set of these low-energy transfer opportunities.
That's the idea. It dramatically increases the number of ways you can navigate the system using very little fuel. It opens up this incredibly complex, but potentially very efficient network of gravitational channels.
Which brings us right back to Jupiter.
Yeah.
You mentioned research from the Beijing Institute of Technology.
Yes, exactly. Their work really focused on leveraging these moon interactions. They ran simulations specifically looking at a flyby of Callisto, which is one of Jupiter's big moons.
And what did the Callisto simulation show?
It showed, and I think their term was a striking reduction in the delta, that's the change in velocity, basically the fuel needed to get a spacecraft into a stable orbit around Jupiter.
A striking reduction just using Callisto. And Jupiter has, what is it now, 97 confirmed moons?
97, that's right. So you can imagine if one moon offers that kind of saving.
The possibilities with dozens,
Right.
It becomes almost exponentially complex, but also exponentially efficient.
That's the potential, yes. An incredibly rich landscape for mission planning. Finding the optimal sequence of moon flybys could save enormous amounts of fuel.
Is anyone actually planning to use this for Jupiter yet? Like the G-USEN mission?
Well, that's the thing. This research, or at least its implications being fully grasped, came a bit too late for JUICE. JUICE is already on its way using more traditional gravity assists.
A missed opportunity for that mission then.
Perhaps. But it definitely raises the question for future missions, the next generation heading to Jupiter or Saturn. Will they be designed from the ground up to exploit this intricate dance with the moons?
It seems like they'd have to consider it, given the potential savings. Now, this idea of using celestial mechanics and flybys, does it have applications beyond just getting into orbit around planets?
It does, actually. There's a fascinating connection to a much older, kind of wilder idea about capturing objects from outside the solar system.
Capturing interstellar objects, how?
There was a paper back in 1979 by Jerry Klein. He proposed, theoretically, that a system like Neptune and its large moon Triton, with Triton orbiting Neptune backwards, could potentially act as a natural trap.
A trap for interstellar comets or asteroids.
Exactly. If an object came in from interstellar space at just the right speed and angle, a flyby of Triton could potentially slow it down just enough for Neptune's gravity to capture it permanently.
Wow. So the moon flyby acts as the crucial braking mechanism.
Yes. Now, the odds of that perfect alignment happening naturally are incredibly slim, obviously, but the underlying physics using a moon flyby to drastically alter an object's energy and trajectory is the same principle we're talking about for spacecraft.
It shows how these gravitational interactions, these flybys, can fundamentally shape what's possible, not just for us, but for the cosmos itself, creating these gravitational traps.
Precisely. It connects the practicalities of mission planning back to these grander celestial mechanics.
So let's pull this together. What's the big takeaway here for the future of space exploration?
I think there are two main things. First, the obvious economic benefit. Harnessing moons for these gravity assists could dramatically cut fuel costs, making ambitious missions much more feasible.
Opening the door to more exploration just by being smarter with fuel?
Right. But second, it's not just about saving money. It opens up a whole new playground for astrodynamics, new types of orbits, new ways to move around complex systems like Jupiter's. It pushes the science forward.
It feels like this could become standard practice.
Yeah.
Will future interplanetary missions almost have to use moon flybys if they're available?
It seems increasingly likely, especially for the outer planets. Why wouldn't you use such a potentially powerful tool? It might even, down the line, make things like capturing asteroids or maybe even rogue objects seem less like science fiction.
Lowering the barrier to entry for exploring the solar system and maybe beyond.
Absolutely. It really changes the calculation of what's reachable.
Yeah. So maybe a final thought to leave everyone with. What does this intricate gravitational dance really signify for us?
I think it signifies that the universe provides these subtle solutions, these efficiencies, if we're clever enough to find them.
Yeah.
Every time we figure out one of these gravitational handshakes between a spacecraft and a moon, we're not just saving fuel.
What are we doing?
We're getting a step closer to making the vastness of space feel a little less vast, a little more accessible. It fundamentally changes our relationship with distance and possibility, moving missions from just possible, so maybe truly affordable and routine,